Welcome everyone. In this video, I will explain what is instruction set and how to write assembly language program for x86 processors. As this is the first lecture video on this series, I will be taking very simple examples to show how to start writing a simple program. Now, before we go and start writing a program, first of all, I will go through quickly the different types of instructions. So, what is an instruction? Basically, instruction is a command used by a processor to perform a specific operation. x86 have more than 20,000 instructions. Yes? So, we have to understand a little bit about these instructions. Like, the instruction could be a data transfer instructions. So what a data transfer instruction does, it basically transfers or copies or move data from one location to another location. Few examples could be move instruction, push or pop instruction, in and out instruction. The details of these instruction we'll discuss slowly as we move on. Next type of instruction which is very useful or widely used is arithmetic instruction. As the name says, it is used to perform arithmetic operations like addition, subtraction, multiplication, division, increment, decrement. So these are the examples of arithmetic instructions. Here I have given them in the way they are being used in our x86 processor. Add, SUB is for subtract, MUL is for multiply, divide, INC increment, DC decrement. Yes. Then the next instruction in this category would be logical instruction. So basically, logical instructions are used to perform logical operations like AND operation, OR operation, NOT and XOR operation, and many more. You have already studied in your digital design course what these logical operation mean to you. Yes? Then I will take up branch and program control instructions. So basically, these instructions are used to branch or transfer the control of your pointer to another location within the program and execute the program. Like few of the examples could be your jump instruction, loop instruction, call and return instructions. So broadly, we can classify our instructions into these classes. There are many sub classifications also available, but at this stage, I will not go to discuss those things. Let us start with a very simple yet frequently used instruction, which is move instruction. The format of writing move instruction is move destination, comma, source. Move destination, comma, source. In this instruction, the data are called as operand. And the operation performed is called as opcode. Hope you have watched my previous video on addressing mode, which explains clearly the difference between opcode, operand, and different types. Now, when we write move destination, comma, source, the first data here you are writing is your destination, and the second data here is your source. So what this instruction does, it copies the content of source to destination. Yes. Then, as it is a data transfer instruction, it does not affect any of the flags. We should know that arithmetic and logical operations are going to affect our flag, because for any arithmetic and logical instruction, we are going to perform some operation on data. that uses your ALU, arithmetic and logical unit. So it affects your flag. As move is a data transfer instruction, it does not uses ALU, so no flags will get affected. The important point here to remember is the size of your source and destination must be same. Source can be a register, memory, or immediate data. My destination can be a register or a memory location. Now, coming to different types of move options possible are, I can write the data is being copied from memory to a register. So example of this could be, I will write move AX comma a address memory location 1234H. Let the address or the memory location 1234H have a data 1234H have a data 8CH in it. As we know, the memory is byte organized. Any address you consider, this address is capable of storing 1 byte of data in it. So, in this example, the address which I am talking about or the memory location I am talking about is at an offset of 1234H and it have a data 8C stored in it. So when I write move AX comma within square bracket 1234H, square bracket represents that it is a memory location. Yes. So the content of this particular memory location, which is 8C, will be copied onto AX register. Similarly, I can transfer data from a register to a memory. So we can write move 1234H comma AX or register to register move AX comma BX. In this instruction, the content of a BX register will be copied into AX register. Similarly, you can transfer immediate data to a memory location or immediate data to a register. The example could be move 1234H comma 8CH. So the data, which is immediate data we are writing 8CH is directly copied onto the address or memory location 1234H. Similarly, we can write move AX comma 8C88H. Here, when I'm writing AX is a 16-bit register. So, the 16-bit data or 2 bytes of data is being moved or copied onto AX register. Or you can write move AL comma 8C or move AH comma 8C. So, these are the possible move instructions. Similarly, we can have increment and decrement instruction. I have already given the example. These are your arithmetic instructions. So what they basically do is the content of this register or the memory location will be incremented or decremented by 1. So the format of writing increment instruction is INC destination. Yes. So you can have your destination could be a register or could be a memory location. There are multiple ways of writing the memory location. Here you can write increase BL. So what it will do? Let us assume that BL have a data 23H stored in it. After executing the instruction INC BL, the content of the BL register will be incremented by 1 and now it will be 24H. Similarly, I can write this instruction for a 16-bit register INCBX, or I can write a decrement increase instruction DEC destination. As increment does, just the reverse thing will be done by decrement instruction. It will decrease the content of a register or a memory location by 1. The content of the register or the content of a memory location is reduced by 1. Yes. Now we'll take up few examples of branch instructions. Here I have taken some conditional branch instruction like jump if equal JE is your jump if equal, or JZ is jump if 0. It branches to a particular address if 0 flag is set or if equal condition is met. Similarly, you have jump if not 0 or jump if not equal. So what it will do? It will jump if not 0 to a particular address if the 0 flag is 0. Yes. When the result is 0, my 0 flag will be set. When the result is not 0, my 0 flag will be 0. Yes. And as these are branching and program control instruction, they are not going to use your ALU. So it is not going to affect any of the flags. With these few basic instructions, now we will try to write a simple program. So I will explain what should be the logic or how we are going to write the code part of this particular program. So here the objective of this program is to copy a block of data from one memory location to another memory location. So here the memory locations are given as from 20,000 H to 22,000 H. So I want to copy 50 bytes of data from this location 20H to another location 22,000 H. So the first thing we are going to understand what basically this program will do. So here I am writing that we are going to transfer 32 bytes of data. So when I'm saying 32, this 32 is in hexadecimal. 50 in decimal is equivalent to 32H. Yes. So my source address in this case is 20,000 H. So I am starting from this particular address, and this particular address have a data 21H stored in it. Similarly, the next address 20,001 have a data in it as 22H, 20,002 have data, and so on. And I will, as I have to transfer 50 data or 32 bytes of data, 32H byte of data, I'm looking into that many addresses in memory locations starting from 20,000. So up to 20,031H, this data need to be transferred or copied onto another memory location starting from 22,000. Yes. So after this program, my 22,000 will have a data 21 in it. 22,001 will have a data 22 in it and 32 in it and so on. Yes. So before I start the program, I have to break these addresses, my source and destination addresses, how I'm going to represent it in my program. So in this case, my source address is 20,000 and destination address is 22,000. Now 20,000, I'm going to break it into two parts. 2,000 with 0000. Base address will be 2,000 and offset will be 0. In this case, the base address will be 2,000 and offset will be 2,000. So adding this to the physical address will become equal to 22,000. So as the base address for both this source and destination are same, I can write this address as D, that it will be in the data segment. So DS plus source index. This will be data segment DS plus destination index. So DS will have 2000 in it and SI will be initialized as 0000, DI will be initialized as 2000, 2000. We'll start our program. First of all, I'm going to initialize the data segment. As I have explained in the previous slide, my data segment DS is 2000. The value of your DS is 2000. So 2000, I cannot directly move to my data segment register. This is restricted. So I have to use a general purpose register to copy the data onto the data segment register. So 2000 first, I'm copying 2000 onto a general purpose register AX, and then I'm transferring AX to DS. So once I'm done with this, my data segment register will be initialized to 2000. Then we will initialize our pointers, your source index pointer and destination index pointer. SI is initialized to 0000 and DI is initialized to 2000. So that DS plus SI gives me a physical address of 20,000 H and DS plus DI gives me a physical address of 22,000 H. After initializing my addresses, I would have directly copied data from my source to destination. But if I see the program clearly, both my source and destinations are memory locations. So you know different formats. In the previous slide, we have discussed that the formats of move instruction, we do not have M to M move instruction. That means move instruction, we cannot directly transfer data from one memory location to another memory location. So what we need to do is we have to transfer data from source memory address to a general purpose or temporary register, and from that temporary register to a destination. And how many times we have to do this? We have to do it 50 times or 32H times. So for that purpose, I am initializing a counter here. CX register is used as a counter here, and it will keep the track of how much of data transfer has been done. So CX is initialized to 0032H. Now, I will start copying data as I have shown in the previous slide. The data at 20,000 H should be copied to the address 22,000 H. Yes. Then I will go to the next address, which is 20,001, and the data present in that location will be copied to the address 22,000 H. Yes. So I will keep on repeating this process 32H times. So here I am going to use a looping instruction. Yes. So I am writing X1. Here X1 is a label assigned to a particular memory location because these set of instruction I want to repeat. Yes. So move BL comma within square bracket SI. What this particular instruction will do, as we have already discussed, memory to a register. Yes, the content, whatever is present at this address location, SI is my source index or source in this case. The data present in this particular memory location will be copied onto BL register. Yes, so the transfer of byte of data to a BL register. Then I am copying that data from this temporary register BL to my destination DI. Move within square bracket DI comma BL. So this basically completes the copy of first byte of data from my source address to my destination address. So one byte of data transfer is complete now. So what next I want to do? I want to go to the next address. Again, take the data from that address to the temporary register and transfer it to my destination. So, as I want to move to the next address, I will increase SI so that if initially SI was 0000, now it will become 0001. I will increase DI, which is 2000, it will be 2001. So I am now pointing to the next address in source as well as in destination. And how many data transfer we have completed? We have to decrease our counter by that amount. So here we have completed 1 byte of data transfer. So I should decrease CX. And this will continue. These instructions will continue as long as I have transferred the entire 50 bytes of data to my destination, or 32H byte of data to my destination. So the CX register is going to keep the count, and the flags I'm going to use after the decrease CX instruction. So as this increase and decrease are your arithmetic operation, they are going to affect the flag. So the last flag affected is due to the instruction decrease CX, and I will check whether the zero flag has been raised or not. So I will repeat this instruction as long as CX is not 0. So jump if not equal to 0 to x1. Yes. So as long as CX register, the content of CX is not 0, the content of CX is not 0, my 0 flag will not be set. And as long as it is not set, jump if no 0. 0 flag will be 0, and it will be satisfied by this particular condition, and the control will be given back to the label x1. Yes. So we will go back to this particular memory location and repeat the instruction. Hope this example is clear to understand. And in my next few videos, I will take up few more complicated examples. Thank you for watching my video.